What you're seeing here might look like something that a cat barfed up, and that's actually because it kind of is. It's a visualization of a cat purring, and my nominee for the coolest sounding thing in all of data analysis, the shadow manifold. And it's what today's video is about. You see, I'm not a big fan of how we teach physics to non-physics students. Truth is, I genuinely don't know how inclined planes will ever be relevant to you. But that's not fair. It's not like we can't find topics for those students that they'd actually care about. Context matters. So in that spirit, today I want to look at the one thing I truly care about, the emotional well-being of my friends' cats. For example, I found that petting a cat makes them purr about 3 Hz faster. Whether that's because of appreciation or agitation, more research is required. But today, I want to talk about something a bit different. I want to talk about chaos. Because while chaos theory might sound kind of scary and abstract, it's actually really simple, and really it should be called everyday theory. Okay, maybe not, but that's really what chaos theory is. It's the study of all the stuff at the human level. And it's hard to think of something more chaotic than a cat. But can we prove that they're chaotic? So in today's video of getting my friends to send me cat pictures masquerading as an education video, we're going to look at whether cat purring is chaotic. After all, if cats are chaotic even in their most cuddly sleepy state, it follows that they must be chaos incarnate. But this stuff is also useful in a more traditional sense. For example, both of these are made from heartbeat data, and even without any idea of the techniques involved, I bet you can probably guess which of these correspond to a healthy patient and which might have some problems. Usually I like to start my videos by talking about the data and how we obtained it, but I just pet some cats. Olga here doesn't really purr, though she does often sound like a car trying but failing to start. My sister's cat Helga, on the other hand, is a purr machine. And this is how the waveform of a purr typically looks like. Notice how it keeps flip-flopping back and forth? Keep that in the back of your head. Now, if we're going to try and test for chaos, we should first establish what that even means, and what better place is there to start than the start of chaos theory itself. It's called the Lorentz butterfly, and it's a fairly famous mathematical object. There's a good chance that you've seen it before, but what is it? You see, Lorentz was a mathematician working in weather forecasting, studying computer simulations of convection as well as horizontal and vertical temperature changes. If that means nothing to you, don't worry, same for me. These quantities influence each other, but to really see that, let's take the y value of each plot at a given time and use that to make a single point in 3D space. Now, as we run time forwards, we'll see the point moves in 3D, and if we make it so that the point leaves a trace of where it's been, we get the Lorentz butterfly. And yeah, that's all the Lorentz butterfly is. It's the relationship between some atmospheric variables that Lorentz was simulating. Maybe a point here could represent a cloudy day, or here a sunny one, or snowy, and so on and so on. The Lorentz butterfly just shows how they go between each other, though keep in mind this is just a very simple computer simulation from the early 60s. I'm sorry if that's ruined a bit of the magic for you, but if the Lorentz attractor is actually not very mystical, why is it famous? Well, mainly because of really good marketing, but it's also because it's what started the field of chaos theory, or as it's more popularly known in movies, shows, and books, the butterfly effect. It's supposed to be a metaphor for chaos, the idea that a butterfly flapping its wings could cause atmospheric disturbances that ripple out and eventually form a storm. Confusingly though, the butterfly effect isn't actually talking about the shape of the Lorentz butterfly. Right now, we're seeing the trajectory of the point for just a single set of starting conditions, the 3 numbers that the computer started crunching the simulation from. To see the butterfly effect, we need a second starting point to compare to, so let's rewind to the beginning and pick 2 points just slightly nudged away from each other. That's the mathematical equivalent of the butterfly flapping its wings. Now, when we hit play, we'll see that despite it being a very slight nudge, the 2 points separate, and by the end of the simulation, they're in different places altogether. Maybe here, the atmospheric variables correspond to a sunny day, and here they correspond to a thunderstorm. That's the butterfly effect. But let's go one step further. Instead of just 2 starting points, let's pick 1,000 starting points and pack them together. All of them different, but only very slightly. If we now hit play, we'll see something that I think is genuinely beautiful. This is what it means for something to exhibit chaos. Tiny changes that ripple out into massive differences over time. And this is also the test for chaos. We pick points that are very close together in this weird parameter space and let them change over time. If the system is non-chaotic, the points will stay together, but in a chaotic system, the points will split apart. Conceptually easy, but what does any of that mean for cat purring? Lorentz clearly had much more information than we do. He knew everything about his system. Of course, he knew it because he made it, but with that information, he could make the Lorentz butterfly and test for chaos. But we don't have that kind of information. There's actually a lot that goes into purring, like breathing and the flapping of the voice box, as well as other things that I don't know how to animate. And in theory, we'd need simultaneous recordings for each of those things, but we only have the one recording, just one of the axes. So if Lorentz's perfect knowledge of his system is unrealistic, let's knock him down a peg. What if he only had one of the three curves? Now his data is incomplete and looks more or less roughly like ours does. Can we still test for chaos, even with just 1/3 of the information? Okay, look, here's the thing. There is a stupidly simple thing that we can do. It's just that it's so stupid and makes no sense as to why it should work, and yet it does. It's probably the closest I'll come to calling something magic, and I can't motivate magic to you. So instead of trying to build up to the trick, I'll show you what the trick is first, and I'll leave a hand-wavy explanation in the description for the nerds. Sounds good? Okay, good. Here's our data from the one dimension of the Lorentz butterfly. Copy the data and shift it back by some amount. The amount of shift or delay you choose doesn't matter in theory, but we'll talk about that in a moment. Next, take the shifted data and repeat that one more time. And that's it. It's so stupid. It's so stupid. Oh, okay. Alright, I should go back to the script. Plotting the three curves together like we did before, we get the Lorentz butterfly. Again, this trick is called time delay coordinates because they are coordinates made from delaying the signal in time. The resulting curve is called the shadow manifold, but I also like shadow clone manifold or shadow the manifold. If we compare shadow to the original, we can see that they're not the exact same. Shadow just looks like a much edgier version of the original. But they are qualitatively the same. If the original had 2 lobes, then shadow the manifold has 2 lobes. If the original gathers the 7 chaos, if the original is chaotic, then shadow the manifold is chaotic. Even though we only have access to 1/3 of the information, we can make the shadow manifold, pick some points that are close together, let the system play out, and test for chaos. And that's exactly what we're going to do with the cat data. If the shadow manifold is chaotic, we can conclude that the original was chaotic. But before that, one minor note about the delay. If the delay is too small, then shadow the manifold looks more like shadow the stick. This is actually important because the one condition on the delay is that we can't allow the curve to cross itself. If it did, it would mean that there are multiple outcomes for the exact same state. Fine in quantum mechanics, but this is my sister's cat, not Schrödinger's cat. If we increase the delay, the shadow manifold spreads out, and eventually there's no crossing, and we're good to go. Almost. So it's at this point that you might have a rough idea of what that thing was from the very start of the video. It's the shadow manifold of the cat purring data. But actually, you might be noticing something that seems to contradict what we were literally just talking about. The shadow manifold is crossing itself in the middle here, and that's the one thing that we can't allow it to do. This isn't a problem with the delay though, it's a problem with the dimension. You see, when we made the shadow manifold of the Lorentz butterfly, we knew we needed 3 time-delayed copies because we knew the original butterfly had 3 axes. Had we chosen 2, we would get something that kind of looks like the Lorentz butterfly, but it has crossings. It's only when we choose the appropriate number of delayed copies that we can lift these crossings off of one another. But even in 3D, the cat purr thing, or let's call it Helga's caterfly. Even in 3D, Helga's caterfly crosses itself in the middle. If it's crossing in 3D, then it's certainly crossing in 2D, so that means we need more dimensions. Now, don't worry, I'm not talking about string theory-esque dimensions. This is real and serious science after all. In data analysis, dimensions just means the number of things making up the cat purr. So, what is the dimension of cat purring? Obviously, if we need more dimensions, looking at it to see if the crossings are gone is not going to be possible. But luckily, we don't have to. Imagine someone asked us to deliver some packages to houses 419 through 422. This seems simple enough. Going off the house numbers, we should be able to just hop from one house to the next and we'll be done in a few minutes. Except there's a problem. While the houses all look like they should be next to each other, in reality, they're not. The problem was that even though we were given the correct coordinates in one dimension, meaning the house numbers, we weren't told about the other dimensions, meaning the street. And so we mistaken two of the houses as being neighbors, but they were actually false neighbors. Of course, there's no such thing as a false neighbor. Either you're a neighbor or you're not. So this is an artifact of getting the dimension wrong. And this is the false neighbors test. We just count the relative number of false neighbors per dimension and keep going until we hit 0. If we were only given house numbers, 1/3 of the pairs of houses would be classified as false neighbors. However, if we include the street information, that drops to 0, meaning that the house locations were two-dimensional all along. For the Lorentz butterfly, the number of false neighbors doesn't hit 0 until 3D, exactly what we would expect. For Helga's caterfly, the number of false neighbors never truly hits 0 because of random imperfections in the data, but it drops to around 3% at 4D. Which I felt was good enough, but obviously in a more serious setting that would require more scrutiny. Unfortunately, I'm currently using Blender 3.6, which doesn't support 4D rendering, maybe in the next version. In the meantime, we can use color to give us a sense of the fourth dimension. Assuming that I picked my colors in a colorblind friendly way, you should be able to see that even though the curves cross each other in 3D, they are different colors, which means that in 4D, they're actually moving past each other. And again, the fact that the data is 4D isn't anything weird or strange, it just means that there are 4 different processes going on to generate a purr. For example, the reason the caterfly has these 2 wings is the same reason the original waveform switched back and forth. It's the cat breathing in and breathing out. And I think it's really cool how this technique allows us to see an almost physical representation of these separate processes. The caterfly looks like something you could hold in your hand, like you could 3D print your cat's own purr pattern. No one steal that idea. But with that, I think we're finally ready to test for chaos. Okay, let's put everything that we've learned together. Step 1, pet some cats. Step 2, copy our data 4 times. Step 3, make the shadow manifold. Step 4, pick some points that are close to one another. Step 5, check to see if the points move away from each other. And Step 6, monetize it on YouTube. And yeah, as you can see, the points are not staying together, they're drifting apart, which would suggest chaos. Of course, if this is a real study, it'd be nice to have a single number that encapsulates whether the system is chaotic, and if so, how chaotic is it? Conceptually, the way to do this is to make a ball of starting points, pretty much exactly like we did earlier in the video. Then we let those trajectories play out, but only just for a little bit, so that that ball deforms. Then we can relate the new shape to the original ball using a kind of stretch factor. More formally, this would be called the lyapunov exponent, but this is a YouTube video talking about cat purring, so I'm calling it the stretch factor. Actually, it'd be more correct to call it stretch factors, plural, since the ball could deform along different axes. In the case of the Lorentz butterfly, there would be 3 stretch factors, and for Helga's caterfly, it would be 4, one for each dimension. For example, this ball of points is being squished along all of its axes, which is the opposite of getting stretched, so all the stretch factors are negative. All negative stretch factors means the thing that we're looking at is non-chaotic, because all the points go to the same place. However, if the ball stretches out even in one direction, then it means the points are getting further apart. This would correspond to a positive stretch factor, which is a sign for chaos. And because the system is chaotic, if even one of the directions stretches out, we really only ever care about the largest stretch factor. There is also the boundary case where the stretch factor is 0. This typically corresponds to systems like pendulums that oscillate in some sort of way. Now, for real data, the method of calculating the stretch factor is a bit more involved computationally speaking, but conceptually, it's just testing if the ball squishes or expands. Luckily, through the magic of using pre-existing programming libraries, all we have to do is feed our data into the program someone much smarter than I wrote. For the Lorentz system, we find that the stretch factor is this number that I forgot to write into the script before I went to record this, which is greater than 0, exactly as we would expect. Now for the moment of truth, making the program do the same thing for Helga's caterfly, we get this other number, which as you can tell is greater than 0. Maybe suspiciously so, hold on to that thought. But regardless, that's still a stretch factor greater than 0. So cat purring is definitively chaotic, right? Well, I have to admit this really surprised me. So much so that I forgot to write this part and had to come back to record it. What does it mean physically for cat purring to be chaotic? I actually don't know. I genuinely started this project expecting cat purring to not be chaotic. I was more looking at it as a chance to fanboy about time delay coordinates and to get cat pictures. In fact, in a moment, I'll be talking about the things I tried to do to disprove it was chaotic, but spoiler, it still wound up being chaotic. So unfortunately, I don't really have an answer as to what it could mean, which could be due to my lack of biology knowledge. And that's where today's sponsor— no, I'm just kidding. But it is really why I wanted to come back to record this part, because I think it highlights the importance of interdisciplinary work and working with people that complement your skill set, like a biologist working with a physicist. But that also means being able to communicate with people. Chaos theory sounds cool, and it is cool, but if you can't explain it in simple, jargon-free terms to someone with interests outside of math, and those people do exist, then its application is limited by your own lack of broader knowledge. And that's really all I wanted to say. Go have a beer with a biologist. They could probably use one. So, cat purring is definitively chaotic, right? Well, honestly, what we've done so far is a good first step, but it wouldn't be considered enough. We've already seen with the false neighbors test that the most basic of these algorithms doesn't take into account that your data has imperfections, and accounting for that is very much active research. I did manage to find a publication delving into this which had public code and used a neural network approach to account for these kinds of imperfections. Using this, I found a new stretch factor of about 0.18, still chaotic, but much closer to zero, which makes more sense because of how oscillatory the original cat purr signal is. Even that should be taken with some skepticism. After all, the only reason I used it was because it was public on the internet. Good enough for a YouTube video, but not for real research. But obviously, does it really matter if it's chaotic or not? I mean, to me it does. But let's be real, this was just a bit of fun. Well, fun in a very specific definition of the word. But that doesn't mean that the stuff we saw here isn't useful in other places where it does matter. Going back to the start of the video, we now hopefully know that these are shadow manifolds of heartbeat recordings, and now we know how to perform all the necessary analyses to compare the two. Prediction of seizure onset is also another place where these techniques are being used. It's a bit more involved, but the fundamentals are there. And that's what I think is great about chaos theory. It's math and physics, sure, but if you taught it to a biology student or an economist or someone that just really likes cats, they could all feel like they got something out of it. It's all about context. But the reverse is also true for math and physics students. A lot of physicists consider the discovery of chaos to be of equal importance to quantum and general relativity. But we only know about it because a mathematician went to work outside the typical norm of what a mathematician or a physicist would traditionally be doing. There's a lot of really cool and important discoveries just waiting to be found if we're willing to step outside of our comfort zone, whether you're a physicist, biologist, or really anyone that's just curious about the everyday things around them. Also, real quick, did you know that not all cats can purr? The cat family tree is split based on cats that can purr and cats that can roar. So a lion can roar, but a mountain lion can purr. That's probably the single most useful thing anyone will take away from this video. Nice. That's sure to get me more cat pictures. Now I just have to figure out how to make a video about dogs.